return that size. I have pictures, and they may help explain this. So let me just go ahead. There can be walls, and then there can be non-walls, and the non-walls, if they correspond to the ground, they're a ground-connected set. The non-walls don't always have to correspond to the ground, but if they do correspond to the ground, they're a special instance where they're a ground-connected set. Yeah, I wish it was only the ground and nothing else, but there's all sorts of strange, horrible conditions in the LiDAR data. Like you would think that people wouldn't have ramps leading to from the ground to the tops of their roofs, but then you come across a parking garage and have to come up with a special scheme to combat that. And God forbid you wouldn't think there's vegetation on top of people's roofs either, but sure enough, you start to come up with a general framework. Oh, no one would ever have vegetation on top of their roof, and then all of a sudden those buildings start showing up as vegetation. But so now we're going to go over some pseudo homotopy tree notation. This was the pseudo homotopy tree. I'm sorry. This is the homotopy tree for these surfaces we described here. Now, and if you remember, Z is going to be. You'll notice the Z, which is the surfaces. Those surfaces actually exist at every odd generation, and that's what this is saying here. Z, J is all the nodes in the generation index. So a given generation I has J sub I total nodes, and you can cycle through all of those nodes. And then if you look at every odd generation, you take the union of all of those sets, that is Z. Z exists at every odd generation, is what that's simply saying. And then Z complement exists at every even generation. And these are some properties and some notation. Some other notation is, I told you the subscripts. I corresponds to the generation index, and J corresponds to the node within that index. The superscripts we're introducing here is N corresponds to the number of children a given node had, and M corresponds to that the node index of the parent of that connected set. So for an example here, this guy here has 3 children, so his N index is 3, so it's 1, 2, 3 children. And then finally, the first node within this previous generation was 1, so that's his parent index. It points to the node location within the previous generation. This guy here has a node index of 2 for the parent, because this is the second. His parent is the second index over. And then the last bit that we're going to introduce is the C term. If I say C at subscript ij, I mean that connected set and all of that connected set's children. That connected set's immediate children and its children's children, and so on and so forth. So I have to introduce this because this will be used. These heuristics and notation will be used in just a moment. Remember I said S of Z returns the size of a given connected set. If we took S of C of 1, 2, the C of 1, 2 refers to this node and this node's children and this node's children's children. So if we assume these guys had areas of 3, 4, and 1 meters squared, then the S of C variable would be the sum of those, or 3 plus 4 plus 1. So let's give an example. What does the pseudo homotopy tree have in application towards building detection? One of the problems I was actually having is, by maybe luck or chance, the test set that I had started with actually had a ditch in it. And I thought, you look at the ground, you do region growing on the ground, and just look at all the non-wall triangles on the ground, and you'd get the ground. The problem is in the set that I had started with, there was a ditch. So I got the ground and the ditch, and then everything else I called beyond that was actually building, and that was incorrect because the real ground level existed above the ditch. But the problem is even a little more complicated than that. Sometimes the ground can be partitioned into multiple ground planes. So if you look at a given set, you might have an elevated highway running through it, you might have a river running through it, so on and so forth. And sometimes some researchers will make the assumption that you only have one ground plane in their algorithm, and this is what causes a problem and where you have to be a little bit more robust to accomplish that. So here we have a given sample terrain, and this is a profile view going from straight across like a slice, and this is a nadir view or an aerial view coming from straight down. So imagine this is a building, this is a building, this is a building, and these two. So we have like 5 buildings. Here we have section 0, which is the first ground plane. And what we're going to do is we're going to look at the lowest triangle, the lowest non-wall triangle within the entire set. We'll take the average of the triangle's 3 vertices and look at all the triangles and see if we can find the lowest one. In this case, this triangle will correspond to section 0. Then we'll do region growing on section 0. Remember, this is the terrain in like a continuous fashion, but these exist as irregular points. We're going to triangulate all of those and then start to analyze that tin, which will describe the surface. And we're going to do region growing. We're going to add all the non-wall triangles within section 0. As we do that, we're going to come in contact with wall triangles in sections 3, 1, and 2. What we'll do is we'll add those wall triangles in sections 3, 1, and 2 to section 0's Q. Section 0 becomes a non-wall connected set, and we have wall triangles in 3, 1, and 2. When we finish growing section 0, then we're going to go back in section 0's Q, and then we're going to start to look at all the wall triangles in section 0's Q, which will correspond to 3, 1, and 2. We'll grow through and we'll grow those wall triangles and make wall-connected sets out of those. So now wall-connected sets from 3, 1, and 2 will form, but as we do that, we're going to come in contact with non-wall triangles existence in 6, 4, and 5. Then we add 6, 4, and 5 to 3, 1, and 2's Q respectively, and continue on growing through the process. Again, what is the meaning of this? What have we effectively done aside from differentiate steep sets of triangles from low-level triangles? I argue, and what I've seen in the data is this, is that more features protrude from the bottom of the ground than features protruding from the tops of buildings. In fact, there's a lot of features protruding from the bottom of the ground. You've got trees, cars, people, trucks, and buildings. What do you have on the tops of buildings? You do have a lot of features on tops of buildings. You have antennas, you might have people on top of the buildings, you might have birds, air conditioning vents, and so on. But the proportion of stuff protruding from the tops of buildings is significantly smaller than this proportion of the stuff protruding from the tops of the ground. In this case, you'll notice, arguably, ground sections 0 and 6 have 3 children to them, but the tops of the buildings only have 1 child at a time. But these guys, 0 and 6, have 3 children from there. In actuality, what I've seen in the data is the non-wall connected sets making the ground actually have lots of children, individual trees, cars, and buildings, and so on and so forth. So in an unsupervised detection, we can do a simple thresholding means to identify these ground connected sets 0 and 6. There are some differences, and this is why I've dubbed this concept as a pseudo-homotopy tree instead of a homotopy tree. In the homotopy tree, the root node is unbounded, and the root node encompasses all connected sets. In the pseudo-homotopy tree, the root node is the lowest non-wall triangle in the entire connected set. If that's at the bottom of a ditch, that connected set doesn't necessarily encompass all other connected sets. And even if the lowest non-wall triangle is the ground and it does encompass all of those connected sets from there on out, it's bounded to the data. So it's not an unbounded thing. And the other thing is in the homotopy tree, Z refers to the surface and Z complement refers to an empty void. Now, one of the things that's nice about the way we formulated the problem is the non-wall connected sets and the wall connected sets are mutually exclusive, just like the surface and the empty voids. So in the pseudo-homotopy tree, Z refers to the non-wall connected set, and Z complement refers to the wall connected set. And you'll notice that the Z exists at every even generation, and the Z complement, or the wall connected sets, exist at every odd generation. And this is something important that we'll wind up using later. This is the region growing block diagram that I just mentioned for the creation of the homotopy tree. We start out with the raw LiDAR data. We'll partition the raw LiDAR data into smaller blocks if in the event that it's rather extremely large, the data set. I use a greedy insertion triangulation to triangulate the data set. And then we look for the lowest non-wall triangle. And then if that non-wall triangle will be, if it is a non-wall triangle, and we start out with a non-wall triangle, we'll do region growing to do the non-wall connected set. Then we'll look in that non-wall connected set, and we'll say, do you have any other triangles in your queue? If you do, we'll go back, and this time it's not a non-wall triangle, it's a wall triangle because he was in the queue, and then we'll grow a wall connected set. And then we'll continue through this process until we've grown and formed the pseudo-homotopy tree. Very similar to what I explained for the previous example. So, all right, great. We identified the ground. How do we differentiate the ground between to get the buildings and the non-buildings and all that other stuff? Well, first, how do we identify the ground? We looked at a given connected set, and here I found out that this threshold is pretty low, but I did play with it, and I could get it to be, I could modify it a good deal and still get the results that I wanted. But we look at the total number of connected sets, and if a single connected set has a greater than 5% of the total number of connected sets as its immediate children, we're calling that ground. So if the ground connected set has a lot of immediate children, we're calling that ground. Now remember, the ground connected set can only be a non-wall connected set, so its generation index has to be even, 0, 2, 4, and 6. Then we implement a heuristic to identify buildings. For buildings, what's nice about this framework is we only make a couple of assumptions, but these assumptions aren't necessarily based on the shape of the building. We don't care about the shape of the building, which is nice. So if the building is curved, if it's irregular, if it's high or low or whatever have you, the exterior contour of the shape is meaningless. What we care about is that the building has a roof and that it at least has 40 meters squared in its area that it's covering. The National Association of Home Builders estimated in 2007 the average home being built was about 226 meters squared. So you can see this 40 meters squared is far below that. So we're able to pick up some sheds, but what I'm arguing here is this 40 meters squared is pretty low, given that the average size of the home being built in the U.S. is 226. So we're saying the building has to be at least 40 meters squared. And what we wind up, I introduced this P index, and this P index simply says that the wall-connected set has to be a first-generation connected set. The P index points to the parent, and in this case, this P index is restricted. The parent index is restricted to only pointing to ground-connected sets. If you look up in this example here, the P indices would only be 0 and 6, so therefore the first-generation connected sets would be 1, 2, and 3, 7, 8, and 9. This is a non-wall connected set. This is a non-wall connected set. They both are identified as ground, and then wall-connected sets 7, 8, 9, 3, 1, and 2 are immediately adjacent to 6 and 0. That's the same concept that I'm talking about here. We're restricting this P index, the parent index. It's not M, it's P, and it's P because it only points to ground-connected sets. It's first-generation connected sets. We're saying the first-generation connected sets that are immediately adjacent to the ground. And then we use a C variable, meaning that first-generation connected set and all of its children. If that has an area of at least 40 meters squared and has at least one child, we're calling that a building. The reason I use the C term is because I want to get the 7, the 8, the 9, the 3, 1, and 2, the 7, 8, 9, and the 1 and 2, which are all immediately adjacent to the ground. I'll talk about later how to deal with a 3. But 7, 8, 9, 1, and 2, and then the 7's child, 10's child, and 13's child. So all the way up the tree, all the generation index. And if this building here has at least an area of 40 meters squared, it'll be classified as a building. The reason why we make the assumption that the wall-connected set has to have at least one child is that a building has a roof. In this case, the wall-connected set that's immediately adjacent to the ground, if it has one child, the next child has to be a non-wall connected set. Buildings have roofs. Typically, the tops of roofs are going to be low-level lying triangles, and then you're going to make they'll wind up satisfying the assumption. If they don't have any roofs, this is often conventional of trees. You'll find that trees and vegetation will exist as spikes from the ground. So they'll have a first-generation connected set that protrudes from the ground. They'll have a wall-connected set that protrudes from the ground, but they won't have a child because they don't have a roof, unless the vegetation is really dense. And I'll talk about that in a moment. So basically, if you didn't meet the criterion to be classified as a building, you'll wind up being a non-building. So if the size of the area is less than 40 meters squared, and you'll wind up being a non-building. If you don't have at least one child, again, you'll wind up being a non-building. Typically, the ones with not having one child wind up being vegetation for the most part. And typically, if they do have one child but they're less than 40 meters squared, they'll wind up being dense vegetation or cars or trucks or things like that. But sometimes you'll get dense vegetation that have greater than 40 meters squared, and I'll talk about that. There's a couple of other heuristics and phenomenon that we'll wind up implementing. Let's say you have a first-generation connected set here, and let's say the orange is the ground, the first-generation connected set is a wall-connected set, and then the green is a non-wall connected set. What we'll wind up doing is we'll look at that first-generation connected set, and then we'll look at all the triangles that are adjacent to the floor or the ground, because we can identify the ground, and we'll take the average of all those points that are adjacent to the triangles to the ground, and we'll call that the floor average. Then what we'll wind up doing is we'll say, okay, if you have what you'll wind up seeing